Alright, time for another draftphysics.com video presentation. Debate physics also, but might as well not even say the word because there is no one who will show up to debate. Rational interpretation of the what we can observe, the evidence regarding how reality works. Okay, how the physical universe works. Can't really discuss that as human beings. It's kind of funny. All the crap people will argue, but they won't argue about this. So, all right, on the subject of photons, I think I'll just say, look, this is this stuff here. This is what the universe is doing. This is the energy in the universe. And when some of this stuff moving sticks to an electron or a proton, that moves the electron and proton. So there's rules regarding what sticks and what doesn't, but the simple truth is when a piece of that stuff sticks to an electron and proton, it moves it. And it moves at something less than the speed it's going, which is the speed of light, so the speed of force. So this is force in the universe, and this stuff makes charge, and it makes magnetism, and it makes electricity, and it makes light. And what electrons do to play their part is when they get momentum, when they start moving, they move into one side of the field and compress it. That means the little stuff starts reflecting off of it, right? If it doesn't stick, it reflects. So if it's moving, the idea is its stuff's going to reflect off of it. So depending on how much energy it has to back up its movement, it can make quite a few reflections. So when it pushes into that field, you can sort of understand if something pushed into the field in a direction, it means all the reflections get put in a smaller amount of space. And depending on how fast it's going, it'll compress that space substantially. If it's going very fast, it will take all the reflections and basically push them into a tiny amount of space. And on the other side, right, the side they're going, say if you're looking at the going away side, the going away side is doing exactly the opposite. All the reflections are coming off much later, much slower. Much later is the right term. And so the frequency, the width of the volume that the 10 bits, let's say, that hit, now they're in a big giant volume. So there's only 10 bits in a giant volume, where on the other side of the electron, there's 10 bits in a very small volume. And that's wavelength. That's causing the frequency that creates photons. Okay, so photons are this stuff with a pattern. The pattern being created by electrons doing this. Okay, it's going to take more than one to make a photon. But yeah, one electron does this, and another one a little ways away does this, and another one a little ways away does this. And that pattern hits a surface, dot, 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 and it pushes an electron on the surface. It gives an electron momentum based on that frequency or period. Okay, it's all very technical. You have to watch a few of these videos to get it. I mean, it's not very technical. It's 2 plus 2 plus 2 physics, but you do. It's very hard to do it in 5 minutes, frankly. It's physics. So anyway, so let's get to it. So I guess I don't need to draw that, right? This idea of the compression thing. You can get it, right? Yeah. All right. So, all right. So the fact that they've asserted that photons don't have mass. Now, look, who cares? They're the only thing that has energy in the universe. And so something collects force. Electrons collect it, protons collect it, and when they collect it, your whole big object collects it. Okay? There's only one universe, the little small universe. It does everything first. Okay? Your electrons and protons have to move before you can move. All right. They're just collecting force. So the force is all there is. The little bits moving. That's the only stuff moving. And the matter is dead until force sticks to it. Okay. And so whether or not the force has mass is sort of irrelevant. I mean, the fact that it imposes momentum in a sense, giving a portion of its momentum. So by sacrificing its speed, it pushes electrons, you could argue. So it's sacrificing some portion of its momentum to push a piece of matter. So, mass is a rational component of that. But strictly speaking, photons don't have to have a mass. But it won't hurt if they do. Okay, so we'll read a little of this. It's just that this is all dependent on them having such a narrow view of what a photon is. They think it's some sort of blob, and then they apply rules based on that blob rather than understanding it's a composite object made of just a frequency, a period of time between events. All right, current commonly accepted physical theories. So again, commonly accepted based on what evidence, So somebody just gives them a story, they say, fine. This is the sloppiest trial in the history of mankind, is the trial that science does. You want to see a real kangaroo court? Go listen to a scientist. Imply or assume that photons to be strictly massless. Right, why? Why is it important? We know they convey momentum, so why don't we just stop there and just say clearly they're momentum carriers. Whether they have a mass or not isn't going to matter, because the amount of mass they'll contribute to something like an electron or proton is going to be irrelevant. If photons are not purely massless, their speeds would vary with frequency. So who says? So nothing varies with frequency, right? So it's all the same speed. Everything that reflects is going exactly the same speed in the reflection, right? You throw the ball at 70 miles an hour, and in the little universe, it bounces back at 70 miles an hour, okay? There's absolutely no loss of a piece of force's capacity to move the speed of light until it's pushing a piece of matter. So anytime it's moving freely in the universe, it's going the speed of force. Push it through a wire, then it's an obstacle course. And it's still going that speed when it's free, but it's pushing electrons, and that's what's slowing it down. All right, with lower energy, redder photons moving slightly slower than higher energy photons. So they're just going by the fact that they're measuring momentum based on tipping. So again, we could just make this simple argument. It's not about how many baseballs I throw at a surface to knock something over. It's about how I throw them. So I could throw them the same exact speed, all right, with the same exact momentum, and the fact is I can tip something over, or I can leave it standing. And it's just based on the fact that if I throw them fast enough, then I keep adding energy and knock the thing over. If I throw them slowly, they wobble, and then it wobbles, and then it wobbles, and it doesn't tip over. So they're measuring momentum with a phony way to measure it. And they've done this throughout history. Since Newton's time, they keep contriving experiments like denting clay with round things, like pushing carts on a frictionless surface, all kinds of ways to measure energy that are not scientifically sound. They're not going to get you the right answer. They have a corruption. They have a variable that hasn't been accounted for. And clearly here, they're not accounting for the fact that the whole point of Einstein's paper is to say it's the same energy quanta. They can't have different energy, all right, and they can't move a different velocity. Anyway, relativity would be unaffected by this. The so-called speed of light, right, the speed of force, would then not be an actual speed. Relativity would be unaffected by this. So the so-called speed of light, c, would then not be the actual speed at which light moves, but a constant of nature which is the upper bound of the speed that any object could theoretically attain in space-time. So that doesn't make any sense, right? I mean, if blue light did travel faster than red light, it certainly would screw up relativity. So that's just bullshit. I mean, nonsense sentence. Thus, it would still be the speed of space-time ripples, but there are different ripples for different frequencies. The radio waves would be preposterously slow, and the gamma rays would be preposterously fast. So what are you talking about? I mean, they concede that it changes the speed of the stuff, and then they say it doesn't matter if its speed changes. Of course it matters, because it's not the speed of light anymore. It's the speed of blue light or the speed of red light. Oh, that's just pathetic nonsense. But it would not be the speed of photons. If a photon did have non-zero mass, so now they're saying if a photon did have non-zero mass, okay, so now they're saying if it had mass, there would be other effects as well. Coulomb's law would be modified, and the electromagnetic field would have an extra physical degree of freedom. So again, that's with the assumption that because it has mass, it moves at a different speed. That assumption is nonsense. You throw the baseballs the same exact speed. The fact is you knock something over or you don't knock it over based on the frequency. It's exactly the same momentum you hit the thing with. The momentum didn't change any. These effects yield more sensitive experimental probes of the photon mass than the frequency dependence of the speed of light. So, gibberish. If Coulomb's law is not exactly valid, then that would allow for the presence of an electric field to exist within a hollow conductor when it is subjected to an external electric field. So what exists is all dependent on what you're using to measure something. And so again, our measurement capacity is limited. So the fact that they don't even concede that just makes this such a waste of time. This is like them saying Eddington experiment proves, this is very weak. This provides a means for procession test of Coulomb's law. The null result of such an experiment has set the limit at whatever, minus electron volts, blah, blah, blah. All right, sharper upper limits on the mass of light have been obtained in experiments designed to detect the effects caused by galactic vector potential. Now, can you imagine they're using galaxies? Galactic. Yeah, it's galactic. No. Field would be observable if the photon is massless. In the case that a photon has mass, the mass term 1/2. See, now they got the m squared. I mean, too ridiculous. Would affect the galactic plasma. The fact that, I don't know what this is. The fact that no such effect is seen implies the upper bounds of the photon mass to be whatever, blah, blah, blah. So again, it really doesn't matter. The fact is it conveys a quantum of momentum. So it's a quantum of energy. It conveys a quantum of momentum. But the photon itself is a group of quanta. It's not one quanta. All right, so let's do the historical stuff, because that ought to be even more ridiculous. So right here we have the Young experiment with water waves, clearly demonstrating it's not the same pattern, right? So in light you get the double maxima, big huge difference, really a gigantic difference, not even paid attention to. The fact is the waves end up being very symmetrical, and the same energy goes forward as goes here, as goes here, as go here. Theoretically, it's pretty much the same energy. You don't see that in photons at all. The energy diminishes greatly. The number of photons diminishes greatly as you go further and further out. So lots of dissimilarities, not similarities. All right. So they called this Thomas Young's double slit. And again, if you use the center of the if you used as your mathematical source the center of the opening, and if you use that in your math, you're not going to get the right answer, because it's not where the sources are coming from. The sources are the surfaces. All right. In most theories up to the 18th century, light was pictured as being made of particles. But in what sense made of particles, right? So Newton didn't quite get to the whole frequency stuff, really nail all that down. And that's the important thing to understand, that this is about little bits hitting at a frequency. That's what's deciding. So Newton thought there was such a thing as red light and blue light, like blue photons and red photons and green. That's what he thought, because he didn't have any better information. So he thought they were different actual photons, when no, it's exactly the same stuff. You're just saying I put it at a different frequency, different period distance between the little bits hitting a surface, a different timing that the bits hit at, and that decides what color it is. Since particle models cannot easily account for the reflection, yes they can, so again, more nonsense. Since particle models cannot easily account for reflection, deflection, diffraction, and birefringence, well, that's creating two image thing, I think. Property of a material having a reflective index that depends on the polarization and propagation direction of the light. Well, obviously all that can be explained with particles, but whatever, because that's just talking about phase changes. All right, of light. Wave theories of light were proposed by René Descartes. Okay, Robert Hooke. So these are the two they're mentioning. So that, Descartes really early. Hooke is in 1665, and in 1668 it's, well, they say 78. I think it's 68, but whatever. Christian Huygens. Now, they didn't mention the guy who got labeled with it. I mean, the guy who, look, Leibniz basically was a plagiarist, okay? I mean, he just went everywhere. He heard what people were talking about, and then he decided to say something on the subject. I mean, that's a pretty safe profile of Leibniz. But whatever. But clearly, okay, Huygens said it 10 years, let's see, 78. Now, that's much later. I'm trying to think. Okay, so 86 is Newton. Right? So that's 10 years before Newton published. All right, and it's only one little sentence. That's it, just one little sentence. However, particle models remain dominant, chiefly due to the influence of Isaac Newton. So again, they talk about his influence when they're not. What they should say is the logic of Isaac Newton. He presented very good logical arguments, and he predicted things accurately and all of that. So it wasn't like Isaac Newton told everybody else what to believe. Isaac Newton explained why he believed what he believed. He made a persuasive argument, and they just want to diminish that as, oh, Isaac Newton controlled everybody with his, in the early 19th century, Thomas Young, so again, Thomas Young's contribution was actually garbage. These are experiments Newton had already done. He had already done the single opening and the single impediment. He had already seen fringe patterns. So he's done apertures, all of that. So this wasn't a new phenomenon, okay? And Auguste Fresnel, who did do a lot of interesting things, clearly demonstrated the interference and diffraction of light. So again, it wasn't a clear demonstration because it didn't fit what water waves do. The patterns are distinctly different. And clearly, if you do the single slit with an open slit, you get 70, 80 bars. You do the double slit with actually open slits, you get a clear two patterns. You get an envelope pattern and a little pattern, indicating, yes, that the outside surfaces are making the little pattern, because that's a lot of wavelengths that fit in there, and that the smallest distance between two surfaces is making the envelope pattern, because there's very few locations where there can be a wavelength of difference. So a tiny bit of logic applied to this, and this argument is nonsense. So they didn't demonstrate anything. And by 1850, the wave model is generally accepted. And yeah, it goes through a whole lot. There's a whole lot of time between, 1665 and 1865. All right, James Clerk Maxwell in 1865 prediction that light was an electromagnetic wave, which was confirmed experimentally. And so again, he didn't predict it was a wave. He believed it was a wave, and that was never confirmed that it was a wave. So again, the prediction of Maxwell's equations hey, this is a frequency, and you can have much higher frequencies and you can have much lower frequencies. So you might as well start looking for this other stuff, because this visible light is just a tiny range of frequencies, and there's got to be frequencies going the other way. Now, Newton already had seen that happen, right? They had already done experiments, I think, in Newton's time, where they were detecting heat. Okay, so they would put light through a prism, and there would be this invisible section where there was no color, but there was still an increase in temperature. So clearly they already had an indication that the spectrum was bigger than just red, green, blue kind of bullshit. All right. That light was an electromagnetic wave, which was confirmed experimentally in 1888 by Hendrik Hertz. So again, he didn't confirm that it was a wave. It's just such a lie. He just found the fact that there's these other frequencies, in the radio wave range. And then a few years later, they found, gamma rays. There's this stuff going even faster, the ultraviolet. Detected radio waves seem to be the final blow to the particle model of light. So again, it really isn't a blow. It's just all hype. So it's just like the Chatelier's 1730 clay experiments, denting clay with round objects. It has no integrity as a scientific experiment, okay? It's not telling you what you think it's telling you. All right, the Maxwell wave theory, however, does not account for all properties of light. I mean, light has so few properties, and then they want to give them a whole bunch of properties. Really, all it has is a property, is its frequency, which indirectly creates its polarization. The Maxwell theory predicts that the energy of light wave depends only on its intensity. So there's no such thing as intensity, all right? It's always, the little bits are always just little bits, and it just has to do with how many photons hit a surface. That is, what's the total number of light quanta that hit the surface, not on its frequency. So there's no such thing as intensity. There is just a frequency. Nevertheless, several independent types of experiments show that the energy imparted by light to atoms depends only on the light's frequency. So again, the energy imparted, they're saying that they're calling it energy when they tip something, and they're saying it's not energy when they wobble something. Okay, so the argument is no, it's the same energy. All right, it's just that you're applying it in a way that causes a more dramatic change. But the more dramatic change is the same energy. It just looks different. The gun's recoil looks different than the bullet. It's the same energy. That's been proven. Yeah, over and over. Not on its intensity. Okay, for example, some chemical reactions are provoked only by light of a frequency higher than a certain threshold. So anything that's going to ionize, we already know that's the rule, ionization. So why don't they just say here, the rule is that if you want to create an ion, and ions are necessary to create electricity, right? Electricity is basically ions. That's what's happening across your heart. With every beat of your heart, the surface of your heart is going from positive to negative ions. It just keeps switching. All right? So it's just making ions. Electricity makes ions. Light makes ions. It's knocking electrons. It's moving electrons. And that's all you have to do. And they only have to be an ion for a millisecond. That's all it has to be. An ion for is a millisecond to create an effect to the rest of the universe. All right. Light of frequency lower than the threshold, no matter how intense. So they know that's not even true anymore. That if they throw enough intensity at a surface, the fact is the surface will end up combining some of those low frequencies into a higher frequency object and end up creating some ions. It does not initiate the reaction. Similarly, electrons can be ejected from a metal plate by shining light of a significantly high frequency on the, and they call that the photoelectric effect, on it. There should be a period there. Anyway, so we know that there's two effects. There's pushing electrons, moving them from one atom to another atom. That's the photoelectric effect. And it's also the photoelectric effect that if you do it with enough intensity, you won't just move them, you'll shoot them right out of the material. So if you give them too much speed, the electrons, they fly right out of the material. All right, but it's the same effect. So you're just saying the threshold for making electricity is lower than the threshold for shooting electrons off the surface. That's why you can use a photocell, or you can create photovoltaics that can collect energy in a whole range of frequencies. The energy of the ejected electron is related only to the light frequency. So again, the frequency just has to do with the fact that you're adding energy to a system, and the sooner the system is going to slow down and go back. So the system has a rubber band in it. And the simple argument is that you want to hit it as quickly as possible if you want to get the most reaction out of it. So the quicker you can hit it in sequence, the more the energy all goes into the object you're hitting. And the more you wait, okay, the slower it's going and the less you can add. Okay. So if you hit it quickly, you can give it more of your momentum. All right. Because you won't be countering the counter force. You won't be having to deal with the counter force. At the same time, it's almost like the gravity argument. The faster you can get something to lift off from the Earth, the less gravity technically you'll have to deal with. You're reducing the amount of time you're exposed to the force, and the same is true for electrons. The faster you get them moving out of an atom, the less proton force, attractant force you'll have to overcome to do it. So the faster you can get them going, the less work you'll have to do, because you'll be in their charge field less time. At the same time, investigators of black body radiation carried out over 4 decades by various researchers culminated with Max Planck's hypothesis that the energy of any system that absorbs or emits electromagnetic radiation of a frequency V is an integer multiple of an energy quantum. So the idea would be that, yes, it's about how many bits the photon is made out of. And the number of bits and how quickly they hit a surface will create all kinds of different effects. But the simple truth is that if you have the same number of baseballs and all you can do is increase their frequency, you're not increasing its total energy. You're just increasing how you're going to impose it. So it's like the bullet and the recoiling gun argument again. Obviously, the bullet can do things the recoiling gun can't because it has high velocity. But the high velocity doesn't mean it has more total energy. The bullet isn't going to, move the 10-ton train. All right, as shown by Albert Einstein, some form of energy quantization must be assumed to account for the thermal equilibrium observed between matter and electromagnetic radiation. For this explanation of the photoelectric effect, Einstein received the 1921 Nobel Prize in Physics. All right, so Einstein just took that one logical step further and said, okay, you have to have this conservation idea, and that's all you're doing. You're just conserving the quanta of energy's momentum. All right, since Maxwell's theory of light allows for all possible energies of electromagnetic radiation, most physicists assume initially that the energy quantization results from some unknown constant on the matter that absorbs or emits the radiation. So again, it's a momentum that's hitting, but clearly, again, just has to be understood, the electrons aren't being pushed by momentum alone. Just like you lifting something in gravity, it's not about just lifting it a foot. It's about how fast did you lift it a foot. And the faster you lift it, the less work you'll have to do to raise it a foot. And the slower you lift it, the more work you'll have to do to get it to that 1 foot. And that's the difference. It's not about the energy going in. It's about how you're applying the energy. All right. Where was I? Thermal radiation. Okay, that's it. Since the Maxwell theory of light allows for all possible energies of electromagnetic radiation. So again, it's not different energies. It's just applying the energy differently. And the fact is that there is this correlation between the higher the frequency, the more energy you'll give an electron, the more you'll be able to give it the energy. Most physicists assume initially that the energy quantization resulted from some unknown constant on the matter that absorbs and emits radiation. Okay, Einstein was the first to propose that energy quantization was a property of electromagnetic radiation itself. So the fact is yes, the photon is made out of a compression of force, all right, in the universe, as averse to an expansion of it. So every time an electron oscillates, it's creating a photon in that direction and a photon in that direction. All right, and that are oppositely phased, obviously. So if you could actually wobble an electron, and then you had a mirror here and a mirror here, you would have two perfectly out of phase hunks of energy. Where there's an on here, there's an off over here, an expansion. When this gets contracted, this gets expanded. And so, you'd have them out of phase. All right. Most physicists assume initially that the energy quantization resulted from some unknown constant. We already did that. Yeah, sorry. Although he accepted the validity of Maxwell's theory, Einstein pointed out that many anonymous experiments, abnormalist, experiments not consistent, could be explained if the energy of Maxwellian light waves were localized to a point like quanta that move independently of one another. That's right, they're not stuck to each other, they're free pieces of energy, even if the wave itself is spread continuously over space. And look, the wave argument is defeated by so many things. I mean, the fact is, the shadow thing is a great argument. There's no way. Changing the frequency of the light does not make it harder for the light to bend around a surface. So that's right there kind of ridiculous. If it was a wave, it would bend around the surfaces. And clearly the laser beam is completely irrational by a wave theory. How does the light know not to go outside of that beam? Yeah. In 1909 and 1960, showed that if Max Planck's law regarding black body radiation is accepted, the energy quantum must also carry momentum. So that's the key word. And again, but it's just the wrong way to look at it. Frequency isn't the momentum. The momentum is the quanta. And it just happens to be, though, again, that if you're going to be knocking things over, if you're tipping things, yes, frequency matters. How you apply the force will matter. The faster you apply it, the more effect you'll have, making them full-fledged particles. This photon momentum was observed experimentally by Arthur Compton, for which he received the Nobel Prize in 1927. The pivotal question then was how to unify Maxwell's wave theory of light. So Maxwell's equations are not a wave theory. So there's no waves in the actual equation. So it's just the fact that Maxwell believed in waves doesn't mean the math is wave math. With its experimentally observed particle nature. The answer to this question occupied Albert Einstein for the rest of his life. And clearly he's, again, I'll just quote, 2 years before he died, he's quoted as saying, I've spent my whole life studying photons and I haven't improved my understanding one iota. I don't like what I think. I feel dissatisfied. Clearly stating he's just not satisfied with these explanations. And was solved in quantum electrodynamics. So nothing's solved. And its successor, the Standard Model, which is just a nightmare of mush. So that's terrible. They bring up this stupid Standard Model. All right, Einstein's 1905 predictions were verified experimentally in several ways in the first 2 decades of the 20th century, as recounted by Robert Millikan's Nobel lecture. However, before Compton's experiment showed that photons carried momentum proportional to their wave number, which is just too ridiculous, right? In physics science, the wave number is also known, as the spectral frequency of a wave measured in cycles per unit distance or radians per unit distance. It is analogous to temporal frequency, which is defined, well, forget it, right? Anyway, most physicists were reluctant to believe that electromagnetic radiation itself might be particulate. And again, it's because they just didn't give it any thought. For years I kept trying to do it their way. I kept trying to say, okay, a photon is a thing, all right, one object. And then you come up with this nonsense of having, radio waves, which means there's a 10-mile object flying through space. No way. There's no 10-mile object flying through space. It's 10 miles at the speed of light between the bangs. And that's all it is, between the arrival events. That's 10 miles. See, for example, the Nobel Prize lectures of Wren, Planck, and Millikan. Okay, I guess I can go try to find that. All right, instead there was a widespread belief that energy quantization resulted from some unknown constant on the matter that absorbed or emitted radiation. So again, you don't need any constant, you don't need anything, you just have to understand that electrons are held and you have to push them out of that hold. There's a force holding the electron, and if you're going to move the electron, you have to defeat that force. And the fact is, speed defeats the force, just like speed defeats gravity. If you can go through gravity quickly enough, you won't be affected by it. All right, attitudes changed over time. In part, the change can be traced to experiments such as those revealing Compton scattering. Again, okay, they keep mentioning it, and again, it's a pro-momentum argument, that basically you're conserving momentum. Okay, where it was much more difficult not to ascribe quantization to light itself to explain the observed results. Okay. Because basically the observed results are, you're expanding or contracting the photon. If you're going to change the frequency of the photon, it means you have to expand the space that the energy's in. So if you're going to reduce its frequency, you're going to have to reduce its reflection, and the opposite would be true for increasing. All right, even after Compton's experiment, Niels Bohr, Heinrich blah blah, and John blah made one last attempt to preserve the Maxwellian continuous electromagnetic field of light, the so-called BKS theory. So I never even heard of this. All right, in the history of quantum mechanics, the Bohr, Kramers, and Slater theory was perhaps the final attempt at understanding the interaction of matter and electromagnetic radiation on the basis of the so-called old quantum theory. So I have to go, I guess, to the whole page, but I don't know if I care enough. The important feature of the BKS theory is how it treated the conservation of energy and the conservation of momentum. Well, maybe I ought to go read it because that'll be pretty funny. In the BKS theory, energy and momentum are only conserved on the average across many interactions between matter and radiation. Well, I think that's always true, so there's nothing wrong with that theory. However, refined Compton experiments showed that the conservation laws hold for individual interactions. It's always tricky to have an individual reaction with a photon, as it is a composite object, and really it's just a pattern. And the pattern can be created from, it's like this scatter argument. If I scatter photons from a source, then I lose the image. So if I have an image and I project it and then I use scatter to spread it, the image is gone. But if I use some other mechanism that bends consistently, that doesn't rely on random scatter, randomized scatter, then I can preserve the image and preserve to more likely to see in that sense what you're conserving. Okay, so it's kind of a complex argument. Anyway, however, accordingly, Bohr and his co-workers gave their model an honorable funeral as possible. Nevertheless, the failures of the BKS model inspired Werner Heisenberg in his development of matrix mechanics. Oh, scary stuff. All right. A few physicists persisted in developing semi-classical models in which electromagnetic radiation is not quantized, but matter appears to obey the law of quantum mechanics. Although the evidence from chemical and physical experiments for the existence of photons was overwhelming by the 1970s, this evidence could not be considered as absolutely definitive. So why some evidence is absolutely definitive? So they say the silly wave crap, is absolutely definitive when that's obviously flawed. Since it relies on interaction of light with matter, a significantly complete theory of matter could, in principle, account for the evidence. So they're just wishing. Nevertheless, all semi-classical theories were refuted definitively in the 1970s and 80s by photon correlation experiments. So now we're into the Bell inequality nonsense and the silly... I saw a photon there, and then I measured the same photon over here. I don't think so. Hence, Einstein's hypothesis that quantization is a property of light itself is considered to be proven. So quantization is a property of how a photon is created on a surface, period. The surface creates the photon. So the argument I'm trying to explain is, maybe I'll draw that, is that you don't need a photon to be in the space and then hit the surface. It doesn't even have to happen that way. It's so this is why the experiments fool them. It's because they don't understand that you can have a component of a photon flying through space, and it's just about how they meet on a surface. So I could have an image of something. All right, this is what I was trying to get to with the image crap. And that creates a bunch of this stuff called photons that come out of off the object with a consistent reflection of where there is something, where there isn't, where there's a reflection, where there isn't a reflection. And these are traveling through space, and then they hit a surface, and they make a photon consistent with exactly what went through the space here. And the argument is that I could put a filter in here and screw everything up. Okay, I could put a fog, right? Fog does it. Okay, and I could scatter, okay, all this stuff. And so now I've lost the image. But the fact is what I'm going to end up having is I'm going to have a piece of a photon, right? So if a photon was 3 bits, 1 bit could come from here and hit, bang, right? And I want a period, I want a frequency here. Because all I'm trying to do is create a frequency. And then at a certain distance, I want it to hit again, bang, and that one could come from over here. That one could be the 2nd bit. And then I could have a bang from here, straight. And that bang would be the 3rd. So I end up reduplicating my frequency, which I need. And I also need polarization, so I need these to be out of alignment a little bit. Okay. For me to create electricity. That is, I want to hit the surface and push an electron. And then I want to hit it again and push the electron even faster. And then I want to hit it a 3rd time and push the electron even faster. That's electricity. I have to get to a certain speed or the electron stops. So if I don't get to a certain speed where it actually jumps from one atom to another atom, the electricity stops. So I have to get it going fast enough where it can just keep hopping from atom to atom. That's an electric current. All right. And so if I'm going not fast enough to defeat the pulling force of the atom, I have to defeat that, and then it'll all be conservative. Once I get going, the pulling force of the other atom pulling me towards it will compensate for the force I'm overcoming. So I'm going to gain momentum, lose momentum, gain momentum, lose momentum. but I'm going to make it. I'm going to be able to perpetuate my path. The electron will keep going. That's charge. That's electric charge. It's an electric charge when you keep pushing more electrons in, and they're pushing on each other. So don't get me wrong, but it's doing the same thing. You're pushing it in, and the pressure is forcing the electron to move. With creating electricity with a photon, you're not creating pressure in the substance, you're creating pressure into the substance. But it's going to have the same effect. All right. So yeah, the point I just wanted to make is that the photon can be the product of a non-coherent source. That is, a piece of it can be coming here, a piece can come from here, and a piece can come from here. So obviously when they do some experiments where they say they're shooting a single photon, and what they're really doing is taking a very bright light, shining it through a very dirty material, and what they're really doing is just creating a whole bunch of particles flying off at all kinds of directions, because it's basically a bunch of two-slit experiments in here, a bunch of surfaces that are going to keep bending the path, and so the photons are going to be flying in all kinds of directions, the little bits. The coherent photon, dot, 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 is going to be broken into stuff that's, there's two here and one here, and the frequency is going to be broken. And the fact is you can just recreate the frequency from different locations. But it won't carry image data. Okay, take a little break. Alright, so let's finish up here. Wave-particle duality and uncertainty principle. So this ought to be absolute nonsense. Photons obey the laws of quantum mechanics, and so their behavior, it is sort of interesting that they didn't really talk much about the double-slit experiments, or, and they're really the decisive piece of information that physics used to draw this conclusion that it's a wave. And so their behavior has both wave-like and particle-like aspects. So again, you could always understand particles can look like a wave. So I could say, if we could see the individual atoms that make up the ocean, and then you could understand that each atom is tied to every other atom with a rubber band. Okay, so you can't move, theoretically, I can't take one of the water molecules and move it. Now, if I move it really fast, I can break the rubber band, and a little water molecule will fly off. But we're saying it's basically they're all elastically held to each other. And so the idea is that what's really happening is you're creating pressure in the water. The pressure is going into an incompressible circumstance. That is, there's a whole density of water ahead of it. So it's like a giant mass. And what happens when you bang something into a giant mass? Well, it reflects. It can't push the giant mass, so the energy can't go in, so the energy has to go back. Now, it can't go back because that's where the pressure is, right? So it can't go into increasing pressure. So it only has two choices. It goes up or it goes down. Now, obviously going down is a problem because the bottom of the ocean is there, and that's really heavy. That's the whole frickin' Earth. It can't push the Earth. So that's not going to help. So where does it go? It goes up into gravity. That's simple. And then once it's up in gravity, as soon as the pressure relaxes at all, it's going to go back down again. But the problem is it goes back down. It's got pressure pushing this way. It's got pressure from the ground pushing up. And so it can't go this way because it's non-compressible, so it goes back up again. And so if you saw the actual bits of the wave, you'd say the water isn't waving. The atoms aren't waving. Okay, the fact is that the atoms are doing this. The atom here gets pushed by the pressure, it moves up, it moves back down, and then this atom here gets pushed by the pressure, it moves up, it moves down. So that's what's really happening. The water isn't waving its way, okay? It's just oscillating its way. All right, a few physicists persisted in developing semi-classical models in which photons obey the laws of quantum mechanics. Whatever. So their behavior has both wave-like and particle-like aspects, so just garbage. When a photon is detected by measuring instruments, so let's just understand, The waves can't behave as a particle. It's just a silly idea that a wavicle is flying around being a discrete bit that's going billions of light years through space and it doesn't spread or do any of this. I mean, it's just a nonsense. It has to be corpuscular. It is registered as a single particulate unit. Yeah, so, and it really isn't, right? So we know on the surface, photons aren't as tiny. When they hit a surface, they don't hit one atom. They hit a clump of atoms. So there's a minimum size something has to be for it to collect a photon, right? We don't have any experiment yet where they can show us them collecting a photon with something that's 200 atoms across. Because all they can do then is collect quanta, not photons, just the energy itself, the momentum of the field. All right, so they're not going to catch any blue photons or red photons that way, or radio photons. No chance. All right. It is registered as a single particulate unit. However, the probability of detecting a photon is calculated. So again, this isn't about detecting with a probability. It's about what's the physical universe doing. And the fact is that what it's doing is scattering bits. And then you can collect the bits that are scattered, and there's probabilities to where they're going to be. And the wave doesn't work. So again, in the double slit, the fringe patterns get duller and duller and duller as you move. The wave theory says no, the intensity should stay almost the same because there's no drag in the space. We know space doesn't have any drag against a photon. We know light doesn't diminish in its intensity for any other reason than the inverse square law. That's the only thing diminishing. How much space the photon is in is changing, but the photon doesn't get weaker and weaker. I mean, there's so many arguments against waves that they just ignore because they don't have an argument against, they don't have any counter argument against those arguments, so they don't even recite them. All right, this combination of aspects is known as wave-particle duality. For example, the probability distribution for the location at which a photon might be detected displays clearly wave-like phenomena. So we know it doesn't. The patterns don't match. They don't do the same thing. And again, the wave theory would say the intensity should all be the same. They're not the same. There's clear argument saying, no, it doesn't work. So why you keep claiming you get right answers when you really don't? Such as diffraction and interference. A single photon passing through a double slit has its energy received at the point on the screen with a probability distribution given by the interference pattern determined by Maxwell's wave equation. So again, nonsense. Again, if they measured from the wave source, which would be the open slit, the center of the open slit should be the center of the wave. Those numbers certainly won't. That distance will not give you the right answer. So it's clearly wrong. Let's see what they say about wave equation of Maxwell's. Maxwell's wave equation, or Maxwell's Heaviside equations, are a set of coupled partial differential equations that, together with Lorentz force, form the foundation of classical electromagnetism. So none of those equations have anything to do with the double slit experiment. However, experiments confirm that the photon is not a short pulse of electromagnetic radiation. So where? A photon's Maxwell wave will diffract, but a photon's energy does not spread out as it propagates. Yeah, duh. Okay. Nor does the energy divide when it encounters a beam splitter. So this is the tricky one, right? Because they don't have any clue how beam splitters work. There's not two equal beams. Going through the glass is different than reflecting off the surface of the glass. And especially if it's a half silvered, and it's never half silvered, it's like quarter silvered, then there's clearly going to be lots of spreading in the beam that goes through the glass, and the one that reflects off the glass isn't going to be spreading. Rather, the received photon acts like a point-like particle since it is absorbed or emitted as a whole by the arbitrarily small system, including systems much smaller than the wavelength, such as atomic nucleuses. So we know you're not going to collect a single photon with a single nucleus. That can't give an electron enough energy. It has to happen in a substance. A single atom can't absorb a photon. Okay, it can only absorb quanta. All right, or even a point like electron. Yeah. While many introductory texts treat photons using the mathematical techniques of non-relativistic quantum mechanics, this is in some ways an awkward oversimplification, as photons are by nature intrinsically relativistic. So no, they're not. There's no absolutely zero relativity. They always are force bits. They're always moving the speed of light, and all they can do is be absorbed by a surface and then re-emitted, or they can just reflect off the surface. But that's all there are. Those are the only two choices. Because photons have zero rest mass, so nonsense again about this stupid mass crap. No wave function defined for a photon can have all of its properties familiar from wave functions in non-relativistic quantum mechanics. So this crap about how the photons can't wear the same colored shirt. It's just too ridiculous. In order to avoid these difficulties, physicists employ a second quantized theory of photons described below. Oh, I'm just so interested. Quantum electrodynamics, in which photons are quantized excitations of electromagnetic modes. So isn't that interesting? Not. So this gets into Feynman's nonsense. You could borrow energy from the future. All right, so I don't even know if it's one more paragraph. I guess let's do it. All right, another difficulty is finding the proper analog for the uncertainty principle. Yeah, there's no analog. There's no uncertainty principle. Things are in real three-dimensional places in the universe. It's just such a pile of crap. An idea that frequency attributed to Heisenberg, who introduced the concept in analyzing a thought experiment involving an electron and a high-energy photon. So again, there's no electron high-energy single quanta of light experiment. There's no, you have to, for it to be a photon, for it to move the electron from one atom to another atom, for it to be a photon, it has to apply the energy to more than one atom. However, Heisenberg did not give precise mathematical definitions of what the uncertainty in these measurements meant. So again, the smallest things in the universe, we can't see them. Oh, gee, let's say they're invisible. Let's say they're anything, right? We might as well just say they have gremlinosity, or hobgoblinness. I mean, you can make up anything because, we can't see them. The precise mathematical statement of the position, momentum, uncertainty principle is due to the, Canard, Pauli, and Wally. The uncertainty principle applies to situations where an experimenter has the choice of measuring either one or two conically conjugate quantities like the position and the momentum of a particle. So again, you can't measure any of this crap for a single photon, so it's absolute nonsense. You can't measure photons. You can't. You only measure it as a collected. You collect it, okay? And once it's collected, it's dead. According to the uncertainty principle, no matter how the particle is prepared, this is just more nonsense, like they can prepare a particle. It is not possible to make a precise prediction of both the two alternative measurements. And again, there's no reason why it wouldn't be possible if we had, if we could see the real micro-universe. If the outcome of the position measurement is made more certain, the outcome of the momentum measurement becomes less so. So this is just a silly thing where, Newton did these experiments where you just change an aperture, right? So in some sense, you're saying, oh, look, it's a smaller amount of space. Its position has gotten smaller and smaller. And so we're detecting its position because we're making the position smaller and smaller. And then we know that means that more photons are going to hit a surface, right? So if I make it smaller and smaller, I'm guaranteeing that more photons are going to go by the surface. So of course their momentum, their direction changes. more and more. As I make it smaller and smaller, I guarantee the photon's going to be disrupted by the surface. And so because that's a correlation, they've decided that this is some sort of phenomenon that is magical, that every photon does it no matter where it goes. So, even when I have a big aperture, somehow photons aren't just flying right through the center, not being disturbed by the surfaces at all, but they're somehow still Heisenberged. No, they're not. And the result will show you that the flashlight will go right straight through the fucking hole. So it's just such nonsense. I mean, they have so corrupted logic here. All right, there is a trade-off reminiscent of the positron momentum uncertainty relation. There's something about quantum optics. Well, let's not even bother. Expressed in the term of uncertainty in the number of photons present in an electromagnetic wave and the uncertainty in the phase of the wave. However, this cannot be uncertainty relation to the canard, it's a good name, Pauli-Wiley type, since unlike position and momentum, the phase cannot be represented by a Hamiltonian operator. Hamiltonian. All right, so, I'm sorry, but the universe isn't this complicated, okay? They've just made a horrible mess out of something that's really, really simple, and they've just turned it into absolute rubbish, and then they just talk with such arrogance that some of this nonsense they're saying has anything to do with this simple universe. This is the universe right here. Simple. Little bits of force traveling the speed of force. They can hit, I can put an object in there, and the object, if it's moving, it'll reflect any energy it runs into. And if it's not moving, it'll absorb the energy. So if it hits with energy going the right way, the way it's going, it'll add to its velocity. If it hits opposing it, it'll subtract from its velocity. That's simple principle. The force tells the matter what it's going to be doing. And every time the matter is doing something, it means the force has been changed. Because now it's slowed down because it's pushing matter around. It didn't get where it was going. Every one of those little bits is going somewhere. If I put a piece of matter in there, some of those bits aren't going to get where they were going, quite obviously, because the matter is going to be in the way. All right, it's that simple. All right. Damn. But how many centuries will it take? I mean, let's say the civilization doesn't fall apart. I mean, realistically, this should not take all this time. It shouldn't take time for the right answer to be discovered by somebody who matters, and then the somebody who matters says, well, look, this answer is so much simpler, and it's so much easier, and it doesn't have all of this fake nonsense operators and all this nonsense. Just so stupid. Just demonstrates our civilization sucks at science. Thank you, Wikipedia, for sucking at science. Science is about having the argument. Science is about testing everything. Science is about having a trial, having lawyers, having debate. Science is about arguing it to death to make sure you got the right answer. Not about cowardly chicken shit who, run away from any controversy. So anyway, shit. Hate this planet. Gotta just make that clear. I have figured out hating this planet is the right thing to do. Because human beings just, 100 billion neurons, and they still can't add 1 plus 1. Sad truth. They think it's 4. 10 pounds plus 10 pounds somehow equals 40 pounds. That's what they think.